remember, right? 6-1, right? Standard normal, right? So we said we know certain things are distributed normally. We spent a lot of time thinking about one very specific distribution that was both normal, right? Which meant it had the bell shape, and was standard, which meant the mean was 0, standard deviation was 1, right? Then we expanded that to not standard, right? This is just not going to work. It's nice outside, but that's just too loud. Right? So what's today? Well, we're going to be looking at sampling distributions and estimators, right? So just a reminder, a sampling distribution, right, is, right, a distribution is when we look at how members of a population vary, right? So I could collect everyone's height in this room, and I could create a distribution. We could look at what's the mean of that distribution, what's the standard deviation of that distribution, right? Another thing I could do is I could take, instead of taking every person in this room, I could take every combination of two people in this room, right? Could take pairs of people. You would be in and I could take the mean, right, height of that pair, right, average your two heights, report that number, right? Then I have a list of means. I can take the mean of those means, right? And I could also take the standard deviation of those means, right? So we're going to be looking at things like that, right? How do those things come in? And the cool thing about that is that if I take enough, a big enough size of those means, right? You really have to do everybody, but those things have a distribution that looks normal even if you didn't start out with a normal distribution. So that's why the normal distribution is so useful, right? It comes up in many contexts. So we're going to describe the sampling distribution of a statistic, right? A statistic meaning some sort of measurement of a sample, right? So if I'm interested, right, if I take the mean of everyone's height in here, that is a parameter. If I'm only interested in, well, if there's some absent students, but if there weren't, this class, right? If I'm interested in the whole population of the university, the whole population of college students in Chicago or whatever, right, then it's a sample, right? Or if it's everybody in the world. So we're going to talk about whether the statistic of a sampling distribution is a good estimator for the population, right? And it's hard to even understand what the hell that means just yet, right? But I promise you by the end of what we're talking about today, it should be a little more clear, right? So again, right, remember, right, we are looking at the distribution of a statistic, right? So there might be many different right? But there will be one, right? So we're seeing how are the different, like, how do these, what's this relationship, right? Where the x mean is the populate, right? And each x mean is of a group that's the same size, right? So this is an example of one, right? We want to figure out how does this end up being an estimate, right? If I take 200 Americans, right, I have a sample. This is my, eventually what we're going to do is, okay, so I know this is my x naught for one group. I know this is S, right? What would be my best guess for the mean? Turns out you're just going to guess that sample, right? This one, though, not quite as clear. We're going to talk about how to figure that out later, all right? So, right, take the process, right? Choose some number n that's not 1, right? And is an integer, positive integer, right? We can take, let's do something that has a mean, right? We can take groups of 7, right? Take 7 people, collect their heights, mean that, right? Mean those 7 people's heights. Boom, take that group. That's a sample mean of one group, right? We can take another group, and that group is not necessarily, and they're not overlapping, right? And in fact, there won't be, because you want to sample all the groups, right? So if I took all the groups in here of size 7, Frank would be in a lot of different groups, right? So with the combination of Frank and Ariana, there'd be in a lot of different groups. So Frank is going to be, his height will be part of many different mean heights, right? And I can plot all of them, right? Now, what it happens is that one, right? Height's not the best example for this because heights are typically normally distributed anyways. But even if it weren't, right? If it were the number of something that's not normally distributed, let's say the well, you guys are too young. Income of your father, right? Those are not normally distributed. There is a long right tail, right? Because you can't make negative money, but you can make a lot of money, right? But even if you do these sample means, that distribution will look more and more normal the larger sample size, the larger number of values is made up in each of these x primes. Same thing for proportions, right? So we'll mention this. The population proportion is lowercase p, right? So let's say p is the percentage of people who have been in a car accident, right? That might be, say, for the whole population, that might be 0.2, right? But I could choose a group, right? Let's say I'm choosing samples of size 10, right? I could have some 10 people, maybe for some group, they might have 30% might be in a car accident, have been in a car accident. Some other groups, right? Maybe only 10% had been, right? But what will end up happening is you will have a normal distribution, right? Centered at this point too. We'll talk about that. Finally, right? Since I'm talking about groups of people, right? This thing you don't have, right? Every person has a height, right? So a group of one person, right? I'm 6 feet tall. If you're talking about a group that's only me, the mean of this group that consists of just me, 6 feet, right? Because it's the only one person in it. I don't have a variance of a height, right? The small group, right? Me and Ulysses, we would have a variance, but it's not very meaningful with 2 people, right? So think about larger groups. You have n people, right? You have multiple people in the group, you will have variances, right? Remember, the bigger the variance, the bigger variation we expect in that group. This one is weird, right? The distribution is not normal. You will have a long tail that includes higher variances. So it's a distribution that's skewed right. But the sample stuff is a little bit difficult to even like kind of wrap your head around. So I'm going to try to get to that in a little bit. So I want you to understand what it means to be a sampling distribution of the sample mean, right? I get different groups, the same size, right? All the different possible groups, and I take the mean, right, of whatever I'm measuring, let's say height, right, of the samples with the same size. I write all of those samples down. This group has a mean height of 5'10". This group has a mean height of 5'9", 5'5". What would we notice? The distribution of sample means tends to be normal, and the sample means tend to tend to target the value of the population mean, right? This is hard to see without having an example, okay? So let's just kind of try to give an example, right? So let's consider this process. So there's say that this dice has been rolled many, many, many times, right? I can roll a dice 5 times to randomly select 5 values from the population, right? And then find the mean of each of these results, right? So let's say I roll the dice 5 times. I get a 3, get a 5, I get a 1, I get a 2, I get a 2 again, right? Add these together, 3 plus 5 plus 1 plus 2 plus 2, right? That gives me a total of 13. Divide that by 5. I'm going to get 2.6, right? So this is a figure that happens when I do what I just described, right? That was me doing it one time. I could do this 10,000 different times, right? So there are two numbers here, right? Notice one is the number of rolls in each trial, right? That's 5. Number of trials is 10,000, right? So each value here is the mean of 5 different numbers, right? Now, each number is warm in this room no matter what happens. I'm trying to draw a normal distribution. I'm failing a little bit here, but you get the idea, right? Each of these bars would have the same height, we would assume, right? But, and in the middle, right, the mean of these would be 3.5. But it would be uniform. Now, if I roll my dice 5 times in a row, I am not, if I roll my dice once, I'm as likely to get a 6 as I am to get a 1. Would we all agree with that? As I am to get a 3. Right? But if I roll the dice 5 times and average those out, am I as likely to get a 6 as I am to get a 3? Well, I would say no, right? To get an average of a 6, I would need to have all 5 of those rolls be, each of them be a 6, correct? Right? But to have an average of, say, 3, I could have some 3s, some that are less than 3, but those would be made up for by also having some more than 3, or they could all be 3. There are more ways to have an average of 3, right? So I would have more bars in the center, would have higher bars, and shallower out on the edges, right? So this would look approximately normal, even though it's coming from a distribution that is uniform, right? And let me again remind you how I make these sample procedures, right? I am taking different samples, right? And each time I roll the dice 5 times, right? So I'm taking a sample out of my big set of 5. I'm averaging, I'm getting the mean from that sample, and then I'm plotting the mean, right? Then if I look at the mean of all of those means, I will end up getting what should have been my original mean. 3.5. Right? Because each of these values are equally likely, the mean is 3.5. So we see that that's the number that's in the middle of all those, right? You could also figure that out using a probability distribution. Remember, the mean of a probability distribution is equal to x times P of X, right? For this, there are 6 different values, right? Each of them has a probability of 1/6. So that gives me 3.5. So that's the mean. And if I did this process, right, where I mean out 5 things, some means would be like down here in the 2s, some would be more, but the mean of all of those means would be 3.5, which is the same as the mean of all the dice rolls, right? So the mean of the means is the same as the mean. Clear as mud, right, when you say it that way, but that's what I'm saying. However, the distribution of these would not be the same. The distribution is approximately normal, right? While the original distribution, right, the distribution from just individual rolls would be uniform. It would be flat. Any questions here? Going to make sure we're all paying attention. Okay, so here's what I want you to discuss, because I know sampling distributions are confusing, right? Explain a sampling distribution, right, by referring to this process here, right? Explain what it means and explain what's going on here and why we see kind of the pattern we do, right? And then I want you to imagine, then I want you to ask, right? So notice here, n is 5, right? Each of these is an average of, each mean is an average or a mean of 5 different rolls. How would this look different if n were 10 or n were 100? If you don't quite have the answers on there, you can kind of answer yourself 3 things, right? Would the center of the distribution change? Right? Would the shape of the distribution change? And would the spread of the distribution change, right? Does everyone kind of understand what they're being asked to discuss? At least some of it? All right, so let's try to discuss that. I'll take attendance and then we will talk about this in a little bit, all right? Let's get to work on that. Let's hear some discussion. At least try to explain what is being done here. How do we go from the blue to the green to the red? You should know because no one asked any questions. Okay. So let's talk about this now. So just to review how we're getting these, right? Each time, right, I'm rolling a dice 5 times, right? It's like I'm taking a sample of 5 from all the possible dice rolls out there, right? Sometimes some of them are 1, some of them are 2, some of them are 3, right? They'll have different means, right? The mean will be ranging from 1 to 6, right? And I can plot each of those means, right, and record how many I have of each value, right? So I will have 3.4 some number of times, 4.4, etc., right? Now, when I do that, I will get fewer on the edge than in the middle, even though when I do it just once, I have the same amount of each value, right? Because think about it. If I'm adding up 2 dice rolls, right, I'm more likely to get a 7 than I am to get a 12, right? So when I average them out, they're going to be higher around the middle, 3.5, than the edges, right? So that's one thing we notice. So let's think of some other things, right? As I go from 10, if I roll 10 times and average them through, right, is my average, is the mean where these things centered, is that going to change? No, Frank is correct. It's not going to change, right? And it doesn't matter how many times. Because, right, we are still averaging over dice rolls that are part of the larger thing. So they should stay the same. Now, they will also, the change will change a little bit, but it will still be symmetric and bell-shaped, right? But over time, right? So the larger that n is, the more normal this thing becomes. So it says approximately normal, right? How approximately? Well, it depends how large n is, right? The other thing is, let's imagine this. So rarely do I have something that is over 5, right? An average over 5, because that means I probably have mostly 6s and 5s in my rolls, right? What will happen as n gets larger, right? The amount of dice rolls in each sample. Will we expect as large of a percent of them to be on the edges? Do we think that will go up, down, or remain the same? It will go down, right? We will have, so as n increases, this thing will become more normal, right? And more narrow, right? But it will still stay bell-shaped, right? I actually have a pretty good example of one later that we'll do numerically, but so here's an example, right? So this is the individual, right? Ignore what part of the graph is shaded, right, for now. But like, this is, if I took the individual weight of adult males, that might have a mean of 180, roughly 190, right? Pounds. But I'll have a bell shaped, right? Some people will weigh a lot more, some will weigh a lot less. But if I take 27 adult males and I find the mean of their weight, it's much less likely that the mean of their weight will be much, much larger, right? Because, you know, it's just less likely. You're more likely to get one really heavy or one really on-heavy, one really light person, right? To have a bunch of heavy people or a bunch of light people, right? That's not likely. You will have some that are above, some that are below, and they will kind of cancel each other out. So when you take samples, right, you go from something, so as n gets bigger, you go from something that looks like this to something that looks like this, right? So let's kind of, if you're still, anyone's still unclear exactly about the process here, let's take a look at a particular example, right, to show you that the sample mean, what it means to target the population mean, right? So this example is one that that has very little practical purpose in statistics, but it's one that has a large illustrative purpose, right? So let's consider that you have this family, right, with 3 children, right? And there is one child that is 4 years old, the other one that's 5 years old, the other one that's 9 years old. So in this case, the whole population has 3 individuals, right? Now, since you have access to the whole population, why would you work with a sample? You wouldn't, but let's just pretend you did decide to work with a sample. Let's decide that you wanted to work with a sample of 2, right? 2 children. And let's say that you choose the children with replacement, right? Like you can choose the youngest child twice. Well, there are different possibilities, right? So let's take a look at this. So here are some different samples, right? And I'm considering order to matter here. You would say it doesn't really need a sample, but it's okay. You could just say I'm considering some samples twice or whatever, right? Doesn't really matter. But for each of these, we can find the sample mean, right? So if I choose the 4-year-old twice, what would be the mean age of the people in that sample? That one's really easy. 4. Now let's look at some other one. If I chose the 5-year-old the first time and the 9-year-old the second time, what would be the mean age of that sample, everybody? 7, right? This one would be 4.5. This one, they add up to 13. So the sample here is 6.5, right? So we can, without wasting too much time, I animated so the numbers would come in there. So these would be the means, right, of each of these different samples. Now, if we want to figure out what is the expected value of the mean, right? We think about right? That is the expected value for anything. Expected value itself is a mean, right? So are any of these samples any more likely than any of the other ones, right? Like, are we more likely to be choosing the 5-year-old than the 4-year-old than we are to be choosing the 9-year-old than the 4-year-old? Is any of these samples like more going to come up more often? What do we think? No, right? Each of these are as equally likely. So how many different possible samples are listed there? 9. So each of them is going to have the probability of what? 1/9. So it's going to be, so P of X for each of them is 1/9. So since I'm taking each of these sample means, I'm multiplying it by 1/9, I'm adding them together, we could factor out that 1/9, right? You calculate this all together. Anyone want to do this for me? How many years do you get? Anyone have a calculator? Anyone got something? What do we get? Participate. We got a number here. It's pretty easy to type in your calculator. You could just add all these numbers and then divide by 9 if you're using your phone. I'm waiting for an answer. That's what's going on. Yeah, Ulysses. Yeah, which is the same thing as 6. Yeah. So I don't know exactly how that happened, but you can imagine there's nothing between 5.9 repeating and 6, so that's the same thing as 6. Okay, so that's 6. Let's now find, so what we call this is, I'll mention this later. I call that mu with a subscript of X bar, right? So this is kind of confusing, right? X bar, right, is a mean of a sample, right? And a sample is not the whole population, correct? So each of these is a sample, right? So each of these is a X bar, right? But these altogether are all possible samples of size 2. Do we agree with that, class? These are all the sample sizes, all the samples of size 2. So this, in this case, right, and I am finding the mean of all of those samples, right? I'm finding the mean of all of the means. So that's why I have a mu here. It is a population of all the samples. Kind of confusing, but do we see how that's why there's both a mu and an X bar, right? Part of it is sample, right, which means not everything, but it's all of the samples, so that's the part that's everything, right? So that is the mean of all the samples. But let's just find the mean of the population. So the population, . let's do that. That's easy. The population has the values 4, 5, and 9, and we divide by the size of the population, which is 3. That also gives us 6, right? So in both cases, we're talking about 6 years. So notice what this is saying is, right? So there's two things, right? What we mean by do these, so the sample means target the population mean, right? Some sample means are much higher than the population mean, but some are much lower, right? And when they're all, I know we don't like to use the word average, but there's no word meaned out. Averaged out, you get the population mean. So the mean of the sample means is equal to the population mean, right? Mean of sample means, right? And we're talking against of the same size. Mean of sample, here's an important sentence to think about it, right? Mean of sample means targets the population mean, right? Or is the population mean, right? These sample means, right, are not all the same, right? Some of them are more, right? Here's a 9. Here's a 3, right? But in the middle was 6. These targeted, they're distributed around the mean of the whole population. Questions here? Great. So then you should easily be able to talk about what am I trying to demonstrate with this slides? What do I mean by the mean of the sample means is equal to the population mean? What do I mean by that? Explain that and explain this process to the person at your table, right? Because this stuff gets confusing because we're using the word mean in several different ways, right? So let's try to make sure we're all on the same page. Does everyone understand what they are supposed to discuss right now? Okay, let's get discussing then. Yeah, so population means just like the mean that we would have found before this chapter, right? The mean of everything. So this would be the population mean because the population just has 3 values, right? This is the population of, this is weird, it's a population of samples, right? Because it's a list of all the samples, right? This is why this section gets confusing because we face things like means of means is equal to the mean, right? That doesn't mean much. Or then we'll later talk about the standard deviation of means, the mean of standard deviation. It gets very confusing, right? So it's good to just kind of stay on top of it. So good question. Okay, so there are variables, right, that, so the mean, right, works, now this was a case of discrete, but it works even better when the distribution is continuous, right? But there are things that are not numerical, right? Ordinal data. What ice cream flavor do you prefer among 2 ice creams, right? Chocolate or vanilla, right? Now, you don't have much numerical, that's not a piece of numerical data if you're talking about just one person, right? But of a group, right, perhaps, right, of you 3, maybe 2 of you prefer vanilla to chocolate, right? So that would be 2/3 or 0.67, right? Roughly, right? So you can talk about a sample size, right? So we use these 2 different notations, right? And you can do the same thing here, right? So P is the population proportion, right? So let's say P represents the proportion of the population that is male. Then P would be, let's just keep things simple, P should be 0.05, right? But I might have one. I could take a sample of 10 people, right? Sure, sometimes exactly 5 of them might be men and 5 might not be, right? But I could take another sample where maybe only 3 are men, right? And then there might be a third sample where 9 are men, right? And there are a finite number of men, right? Even a finite number of people in the world, or in SXU, or whatever you want to consider your population to be, right? And therefore, there are finitely many samples of any size. There are a finite number. It would be a very, very large number, but of groups of 10 human beings I could come up with, right? Come up with a list, write 10 people down, right? Some percentage of that group will be male, right? So we're curious, right? How do these, right? And these may be, samples of 10 people. What portion of them are men? Some will be higher, some will be less. How do these compare to the population? What do I want to say? How do these compare to 0.5? What is actually the population proportion? The proportion of the population that's meant. Does everyone kind of understand what we're talking about here, right? So notice this one right here is a parameter, right? Because it refers to the whole population, right? And therefore, there is only one such p-value. For this, right, there is one for each sample. But since there are many different samples, you can say that there are many different p-hats, which is how we pronounce this. Then we're going to understand the difference between p-hat and p. So here's something that's cool. If you have all of the sample proportions, right? If you have every different group of a particular size, right? Especially with n being higher, the distribution of population proportions will approximate a normal distribution. And that approximation is better the larger the group sizes are, right? So if I have 5 people in the group, right, it can't be that normal anyways, because there's only, right, a certain number of proportions that you could get, right, with 5 people. For example, with 5 people, you could not have 45% of them be anything, right? And they will target the sample proportion in the sense that the mean of all the sample proportions is equal to the population proportion, aka the expected value. So I showed you a picture of this earlier. This notice is basically the exact same pattern we have with means. It's just a different thing that we're measuring. We're measuring a proportion, right? So let's consider the same thing we did with the dice, right? We rolled the dice 5 times before, and we averaged all the rolls before, right? So here, instead of being concerned with, right, what number comes up, we're just curious if the number is odd or it's even, right? So the proportion, let's say the proportion is the proportion of odd numbers. So P in this case should be equal to what? Proportion of odd numbers is simply what percentage of the numbers are odd on a dice. Guys are killing me. What percentage? 50, right? So if I roll a dice infinitely many times, right? If I look at hundreds of thousands of rolls, right? 0.5 of them, that's the proportion of them that should be odd. Do we agree with that? Okay. But instead of, let's say, doing that, like looking at so many, let's look at them at 5 at a time. So I might get a 1, a 3, a 5. Let's say I get a 2, and I get another 2 at the end, right? In this case, p hat, if this is one of my samples, p hat here would be 0.6, right? Because 3 of the 5 numbers are odd. Do we get how I got 0.6? 60% of these numbers are odd, right? So each sample will be some number from 0 to 1, right? It will be either 0, 0.2, 0.4, 0.6, 0.8, or 1. If I do this, right, I am likely to get I'm pretty unlikely, right? I can actually calculate the exact probability, but I won't. So you get a proportion where all the numbers are odd, or all of them are even, or 80% of them are odd, or only 20% are odd, right? You're most likely to get 40% or 60%, right? So notice in the center, again, is the actual proportion, right? So in the center here, is p hat, right? And there is a normal-ish looking distribution around p hat, right? If I say, so here's n being 5, if n were 10, there would be more possibilities, right? It would be less jagged, but it would so it would be more normal, right? More normal. Same proportion will be in the center, right? Same average proportion, but it will also be tighter, which means your standard deviation is going to be smaller. So instead of looking like that, maybe it will look like let's try and make it symmetric. But the bars in the center will be taller, and the ones on the edge will be shorter, and there'll be more bars because, like, with only 5 rolls, right, the possible proportions are 0, 0.2, 0.4, 0.6, 0.8, 1, right? If I do 10, I could have 0, 0.1, 0.2, right? See, there's more possibilities, right? So the curve will be smoother, but more of it will be in the center, right? It's very unlikely to have, so to have 100% be odd, you would have to have 5 odds in a row. With 10, you would have to have 10 odds in a row, right? So the larger n is, the more of the distribution will be in the center, right? And this is, notice, the same thing with as the mean. Questions on this? So we see how this is just very similar to the previous example. So far, we've talked about, right, how do the means and proportions come up, right? But I could also do variance, right? So remember, variances are kind of tell you how large, right? Variance is the square of the standard deviation. So we've got 2 formulas here. This is the population standard deviation. This is the population variance. So here's the population variance, right? And here is a sample variance. So this is a little bit different, which is one thing that's kind of interesting to notice here is for your sample variance, right? If I'm taking the variance of each sample also has a different mean, right? So you're kind of, there's like 2 ways that these things could vary, right? Some will have different means, right? Like, so even though, right, like for measuring, heights, right? Abigail will be in several different samples and she'll have the same X, but how much she contributes to the variance will depend on how tall the other people in the group are, because how much her height minus the variance, right? Well, there should be a square in there, right? That's different each time. So variance, as you might guess, because it's more complicated of a measure, right, has a more complicated distribution. So one thing, the distribution of the sample variance is the first of these 3 things that's not normal. It's in fact skewed to the right. Yeah, feel free to close. All right. It's just hot in here. The sample variance does target the population variance, though. right? So let's consider the same process with rolling the dice, right? 5 times, and this time we're recording the variance of the numerical values, right? So we're not doing the odd versus even thing, right? So we can use this formula we had to get the population variance, what that should be. So remember the variance of a probability distribution is x, probability of x. So it's the sum of the probability of x times x squared, right, minus the mean squared. So same thing for each of these distributions, right? The probability is 1/6, so I could do 1/6, 1 squared, 2 squared, 3 squared. And we know the mean is 3.5. You do this, you will get 2.9, right? Let's go the same procedure. You roll the dice 5 times, and then you do that 10,000 times. So a total of 50,000 dice rolls, right? Each time you take the sample of that variance, right? So you use the formula this, right? And then you would divide by n minus 1, which in this case, of course, would be 4, right? Because n would be 5. That's how these numbers are generated. Notice unlike before, there's really, well, I guess there is an upper limit. I'm not sure. Yeah, so, but in this case, right? So here is the sample variance. It is targeted, so the mean of the sample variances ends up being the population variances, right? So each of these is, oops, this should be an S, right? So this is done many times. Each of these has a distribution, right, that is skewed. So for the first time, we have something that's not a normal distribution. We'll talk much about this distribution later. This is called the chi-squared distribution, right? So it will get, as n gets larger, as n goes to infinity, you end up having the chi-squared distribution, which is a right-leaning distribution. It looks something like this. And we'll learn a lot more about that later, but just know it's a different distribution than the normal distribution. But it still targets 2.9, right? So that part isn't any different. So it still targets 2.9, but the distribution will not be bell-shaped. It will be, well, kind of whale-shaped, maybe, like this is its head, its tail, I don't know. So let me just kind of point something out that you probably already know. So you might not use it. Everything that we've done here, we use statistics you can use statistics to estimate parameters, right? So for example, I could try to use the proportion of a sample, right, to estimate the proportion of the whole population, right? 30% of this class prefers chocolate to vanilla, so does 30%. So I'm going to guess 30% of the whole population does. The mean height of this class is whatever it is. I can use that to estimate the mean height of all Americans. This is the harder one. The standard deviation, the variance of this class is what it is. I can use that to estimate the variance of the entire population, right? So those are examples of estimators, right? So an unbiased estimator, right? Here's the definition. Let me try to tell you what this means, though. An unbiased estimator is a statistic that targets the value of the corresponding population parameter. And what does that mean? In the sense that the sampling distribution of the statistic has a mean that's equal to the corresponding population parameter, right? There are a lot of words there that probably are confusing you, right? But let's say what we meant, right? So we notice in all three of the distributions that I had so far, right? So when I did the mean of the roles, right? I got all these different X bars, right? Some were bigger than 3.5, some were smaller, some were exactly there. But they averaged out to be 3.5, which is the mean for the whole population, correct? So that is why that is an unbiased estimator, right? In this case, since these are centered around the mean, right? It's unbiased, right? Same thing for proportions, right? Those things were centered around 1/2, right? Even in this case. So sure, the mean is a little bit to the right of the top, right? But the mean here, the mean of all those variances was equal to the variance of the whole population, correct? I told you that. You just had to take my word for it. That was easier to see with the mean, right? So those are all unbiased estimators. And that's why we use those examples, right? Use something else as an estimator. It is biased in the sense that it doesn't work like this. These are not all of the bias estimators, but these are some that are. So what does it mean to be a bias estimator? So of all the people in the world, there is somebody out there is a median height, correct? Right? I could take samples of some people in the world, right? Take the median height of each of those groups, right? Create, just like before I was creating sample means, I could create sample medians, right? And then I could take the mean of all those medians. I would not end up with my original median of my population, right? It's the same thing with standard deviation. That's a little weird. I always find that weird because it does work with variance. And this is just the square root of variance, right? So you would wonder why I couldn't just apply a translation to it. It has to do with the skew and everything. We don't need to get into that. I think the one that best shows this is range, right? You can easily see that range is probably the most biased estimator, and I'll show you what I mean by that. So let's consider the dice example, right? So the population of all dice rolls, right? What's the lowest a dice roll can be? 1, right? That's the lowest. And the highest is, everybody, 6. So the range, right? So I'm going to call this the population range, right? Population range for the dice experiment would be what? 5, right? But now, so let's call this, let's say this is equal, so lowercase r is, let's say that's equal to 5, right? Lowercase r being range. We typically don't use a variable for it. let's say our hat is a sample of 5 dice rolls, just like before, right? Our hat, what's the largest our hat could be? The range of 5 dice rolls. The largest it could be is 5, right? And the smallest it could be is 0, right? If I plot, right, my range is, right, I don't know what the distribution is, right? But the largest it can be is 5, the smallest it can be is 1, right? These are our hats. But notice R itself is 5, right? So before, right, the mean of your sample, they group around the population mean, right? Do the ranges of the population group around the range of the sample? No, right? Because the ranges are numbers from 1 to 5, right? And the range of the population is 5, right? So by definition, 5 cannot possibly be the center because it is at the far end of it, right? Do you see what I'm saying? If we didn't know, right? And that makes sense too, right? Think about another example, human height. If I took 5 people, right, and found the range, right? The shortest of those 5 minus the tallest of those 5, that number would not be a good estimator for the range of all the population of human height, right? Do you guys understand what I'm saying? Right? That we would expect that to be much larger. Questions? Do we get what I mean by range not being a good estimator, right? A sample range is not a good estimation for the population range, right? They will not be grouped around the range of the whole population. Just get a lot of blank looks right now. Okay, I want you to turn and talk to your partner. Last, I think, discussion of the day. What is the difference between a biased and an unbiased estimator, right? And use the easiest examples to explain it. Explain why the mean is a unbiased estimator and range is a bias estimator. Does everyone kind of understand what I'm asking you to discuss? Okay, so difference, right? An unbiased estimator is what we want, right? We know that they sample around. If I have a proportion, right, that's a representative, I can guess based on, right, if I have several different proportions, right, I can say that the population proportion should fall somewhere in the middle of that, right? Or if I have, okay, you know, this class, 30% of them prefer vanilla to chocolate, that's, right, might be, if that's the only information I have, I know that 30% is my best guess, right, for the population proportion, right? Same thing with mean and variance. If I know, okay, the shortest person in this classroom is a foot shorter than the tallest person, right? The range is 1 foot. That is not a good estimator of the range of all human height. In fact, we know, right, the population statistic for range for the population has to be greater than or equal to that population for the sample, right? Does that kind of, it's actually just a minimum on it, right? All I really know is, okay, if someone in this class is taller than 1 foot taller than someone else in this class, I know that the range of human height has to be at least a foot. I don't know if it's 2 feet or 20 feet or whatever, right? It doesn't really help us that much. Right now, so just a quick thing on this chapter before we start the next one. Right? When you're sampling, the sample sizes we did, and remember when we did the thing with the 2 children, I had 3 samples that involved choosing the same child twice. So for these theories to work completely, for everything to work completely, right, we want to be sampling with replacement, right? Sampling with replacement results in independent events, which is the assumption that undergirds everything that I've done in this chapter. Now, we typically, when we find a large sample, when we do a sample, we don't really sample with replacement, right? But that's okay, because anytime we want to sample for a population, the population has to be big enough that you don't have practical access to it, right? So if you're looking a sample that is like less than 5% of the large population, you can treat each selection as independent, even if you're doing it without replacement, right? So, right, for example, if I'm choosing a sample of 100 people, right, in this whole country, the chance that if I selected that I would get a sample that has, if I randomly chose 100 Americans, right, and I'm allowed to choose the same American twice, still probably wouldn't choose anybody twice, right? It would make very little difference if I was or I wasn't, because the chance of choosing an individual twice is exceptionally small. Do we agree with that, right? So when we're looking at this, we don't really need to worry about whether it's with replacement or without replacement. That's mainly what's coming from this here. So assume that it's with replacement, so it's independent, but it's actually not, but it's close enough.